Today we're starting our new unit on magnetism, and to start talking about magnetism, we need to find a couple of terms. The first one is called the magnetic domain. Now, this definition, as I show you, is not going to make a whole lot of sense to you until I explain it. Let me read it to you first, and then I'll explain it. The magnetic domain is a tiny little region inside a ferromagnetic material that is represented by an arrow. Now, we got to define another term in order to understand this. If we're defining a magnetic domain in terms of another term that we don't understand, then we better define the other term. A ferromagnetic material is a material that can become magnetized. It's not necessarily magnetized right now, but it can become magnetized. In other words, it can become a magnet. What's probably the most common example of a ferromagnetic material that can become magnetized? Iron, right? Ferro, iron. Alloys of iron as well. Iron, steel. Cobalt is a ferromagnetic material as well, even though it doesn't have anything to do with iron. There's lots of materials that you might think are ferromagnetic that are not ferromagnetic. Copper is not ferromagnetic. Just because something's a good conductor of heat and or electricity does not mean that it's a ferromagnetic material. Clearly, wood, paper, rocks, most rocks are not ferromagnetic. Some rocks are actually ferromagnetic if they contain iron. Yep.
Isn't copper good for magnets, but not for the actual
Copper is good for producing the magnetic field necessary to generate an electromagnet. Yes, that's because it's a good conductor. Electricity can generate magnetism, and copper is a good conductor, so it can generate a good magnetic field. But it's not magnetic in itself. Okay, so if you have another copper wire, it's not going to be attracted or repelled to this magnetic field that was generated by the other copper wire. Yep. Yes. We'll talk about both of those later on in the unit. Electricity can generate magnetism, and magnetism can generate electricity, although it's a little harder to generate electricity from magnetism than it is to generate magnetism from electricity. A bit, not much, but a bit harder. There's conditions, whereas generating magnetism from electricity, it always happens if we have an electric current. We'll get into that over the coming days, though. So it's a tiny little region inside a ferromagnetic material that's represented by an arrow. I'm going to draw a little picture of a ferromagnetic material with the little domains inside it. There's these tiny little regions. We're representing these regions by arrows. Now, I want you to understand here, of course, if you look at this ferromagnetic material under a microscope, you're not going to see arrows. There's not literally arrows in it. The domains have to do with spins of the electrons. But it's difficult to draw that. So we draw it as arrows. Arrows just represent a certain spin. So these arrows are representing the domains for us. It's not what we physically see, it's just how we represent the domains. Now, this ferromagnetic material right now, this piece of steel or iron or cobalt or whatever it is, isn't a magnet. It's not a magnet because the domains are pointing in random directions. It's a ferromagnetic material. It can become a magnet, but right now it's your fridge door, right? It's the leg of your desk. It's not a magnet right now. It just might become a magnet down the road. So how do we make it a magnet? Well, we need the domains to point in the same direction. We need to align them. If we have this ferromagnetic material with all the domains pointing in a random direction, it's just your fridge front. If we have a ferromagnetic material with the domains pointing more or less in the same direction, now we got a magnet. Either a permanent magnet, something that remains, or a temporary magnet. Like your fridge door becomes when you put a magnet on it. Like when you put your little brother or sister's artwork on the fridge door with a magnet, the fridge becomes a temporary magnet with the domains in the steel of that fridge front temporarily aligned like this. Now, of course, this is a magnet with domains aligned. It has a polarity, not a positive and negative polarity, but a north-south polarity. We would define this arbitrarily as the North Pole, and that is arbitrary, right? North is just a word. we defined the domains as pointing towards the north. We could have defined it as pointing towards Bob, but we didn't. We arbitrarily defined that end of the magnet, the way the domains point, as being north. We arbitrarily defined the other end as south. So these domains are going to point inside the magnet from south to north. What do you think would happen if I cut that magnet in half? If I literally took a hacksaw and cut it in half, what would we end up with? A North Pole magnet and a South Pole magnet, right?
Left half would cut the North Pole, right half would go south.
Yeah, exactly. You still have your domains pointing this way. And you would still have a South Pole and a North Pole right here, but because we define the direction of domains as being from north to south, this would also be a North Pole, and this would also be a South Pole. You can imagine these would attract each other, right? Why would they attract each other? Well, it's just like in electricity, opposites attract. Positive attracts negative, when north attracts south. Do you remember electric field lines? We'll deal with this in a lot more detail on Monday or Tuesday, but I want to just touch on it right now. Electric field lines joined up if there was a force of attraction, right? They did not join up if there was a force of repulsion. Can you imagine if I extended these domains here, if I extended the arrows to outside of the magnet, they would actually represent magnetic fields. So the magnetic field would leave this north and go toward the south. The field lines in between would join up, which means we get a force of attraction, which makes sense, right? North and south are going to attract each other. How do you think we make this magnetized? How do you think we get these domains aligned, right? To have a magnet, we need a ferromagnetic material. And we need to align the domains in this ferromagnetic material. What do you think is a way that we can cause these domains to become aligned? Yep.
I think I remember this from probably elementary school.
Yeah, you probably did some of this in elementary school.
I think you can slightly magnetize something by rubbing two metals together.
Okay.
You can also do it by rubbing a magnet against the metal. Right?
Okay, so you're on the right track there. Yeah, Jake? You're also on the right track, but neither one of you are quite right there, but both on the right track. Both good. In order to cause domains to be aligned, in other words, in order to cause a magnet to be formed, you can bring another magnet nearby. Okay, it's not just a matter of rubbing metal against metal. Okay, it has to be a magnetized ferromagnetic material nearby a non-magnetized ferromagnetic material. So if this is our original ferromagnetic material, those domains are pointing wherever, right? If I bring a magnet, which is this guy right here, with the domains pointing in the same direction, if I bring that nearby, that causes the domains in the non-magnetized material to become temporarily aligned. So I'm going to erase these guys and demonstrate that they will become aligned in the same direction. So this thing here that's causing the magnetizing to happen has a North Pole and a South Pole. This thing over here that was just random domains pointing in random direction now has a North Pole and a South Pole as well. And north attracts south. So this thing that was not magnetized has become a temporary magnet. And as a result of that, they will attract each other. You can see the field lines would once again join up. Parker?
So if the names are pointing direction.
Yep.
They align exactly one is the initial magnet?
The second way to produce this magnet, Jake said something about running a current through the ferromagnetic material. He's close, not perfect, but he was on the right track here. We're not going to run a current through our ferromagnetic material. Okay, that's our ferromagnetic material with our domains pointing in random directions. Rather, we're going to run a wire around that ferromagnetic material, loop it around. And that wire is going to have an electric current going through it. That electric current generates a magnetic field. The current generates a magnetic field. And that magnetic field generated by the current that surrounds the wire will magnetize this core, this piece of steel or iron or cobalt or whatever it is that's ferromagnetic. Okay, if that core is not ferromagnetic, You'll still have a magnetic effect here because this coil of wire, we call it a solenoid, has a magnetic polarity. But it's a magnified effect if we have something inside it that is ferromagnetic. And that's how we magnetize that piece of steel, is put it inside this coil of wire. Not run the current through the piece of steel, but run the current through the wire that's wrapped around the coil or wrapped around the core. Monday or Tuesday, you're going to do a little activity, not a hand-in thing, but just a little in-class activity where you're going to experimentally plot magnetic field lines, magnetic field directions. We have these bar magnets that we use for that activity. Sometimes the bar magnets, they've been sitting a while, sometimes they become weak. We have what's called this little device, it's called a high-strength magnetizer. It creates a really, really, really big electric current, which magnetizes these magnets pretty strongly, pretty quickly. Like I can do it for 5 seconds, and all of a sudden I've got a really, really strong magnet. I don't run current through the magnet. I run current through this wire that's wrapped around inside this device. And then I just put the magnet inside that coil of wire. Yep.
How does that work?
Why does it work? Fundamentally, remember I said when we started this unit that electricity and magnetism are related to each other. They're not the same thing, but they're related to each other. Fundamentally, magnetism is caused by electricity. Magnetism is caused by electricity. Okay, when we look at this, okay, electrons moving generate a magnetic field. But even in this situation, remember we said the domains have to do with spins of electrons. It's still an electrical phenomenon that causes the magnetic phenomenon. So to give you a fundamental answer to why does the magnetic field look exactly the way it is, I can't answer that. But magnetic phenomena are due to an electrical phenomenon, always. Even if it's within a bar magnet, it's still due to an electrical phenomenon. Not an electric current per se, but still an electrical thing, electrons doing things. Yep.
Why is it that even after we take it?
3 laws of magnetism now that when you see them, it's going to be a little sense of deja vu for you, I think. Just wrote a unit test on electricity yesterday. For that test, you had to remember that there were 3 laws of electricity. The first law was, well, one of the laws, there wasn't any particular order of them. One of them was that like charges repelled each other, right? Positive repels positive, negative repels negative. Well, just like charges repel each other, poles can repel each other as well. North repels north. South repels south. South pushes south away. You can imagine what that second law is going to be. If like poles repel each other, then opposite poles attract each other, or unlike poles are going to attract each other. North attracts south, south attracts north. With an equal and opposite force? Absolutely. Always equal and opposite, right? On your unit test yesterday, you knew this was coming. 2 charges, they were different values. One had more charge than the other. How do those forces compare? They were equal and opposite. They pushed each other away. They should have been the same value, the same magnitude. Third law. This one's going to sound different in a way than the third law of electricity, but it boils down to almost the same thing. The third law is that charged objects attract neutral objects. Why do charged objects attract neutral objects? Because of a because of a temporary separation of charge. Induction, right? It induced a temporary separation of charge. Well, what do you think the third law here is? We're not going to say anything about charged objects and neutral objects. Rather, we're going to say, Mason, what? So we're going to say that magnets, north poles and south poles, or if you want to just, instead of saying both the north pole and south poles of a magnet, if you want to just say magnets, either end of a magnet, attracts non-magnetized ferromagnetic material. That's important to write the word ferromagnetic in there, because magnets don't attract paper. Magnets attract ferromagnetic materials. Why do they do that? Well, we kind of just described why they do that, right? If a magnet is brought nearby a non-magnetized ferromagnetic material, it temporarily aligns the domains. Kind of like in electricity, when you temporarily separate the charge. It's induction. It temporarily induces an alignment of the domains. It makes this non-magnetized ferromagnetic material a magnetized ferromagnetic material, which is a magnet. Temporarily, right? Not always, but temporarily. Not forever, but temporarily for sure. Just a little bit more to finish off here, guys. Remember, we defined with gravity a gravitational field as a region in which a gravitational force could be experienced by mass. An electric field was a region in which an electric force could be experienced by a charge. Bless you. A magnetic field is a region in which a magnetic force could be experienced by a magnet or by a ferromagnetic material. A region in which a magnetic force could be experienced by a magnet or ferromagnetic material. It's not at all unlike electric fields. It's not the same thing. It's not an electric field, right? But it's much, in many ways, like an electric field, including the direction of a magnetic field. There is a direction, right? Because it's a vector field. These magnetic fields, these vector fields that surround magnets have a direction. I'm not going to define the direction for you today. But remember, they're more like electric fields than they are like gravitational fields, because gravitational fields always point toward what produces them. A magnetic field, like an electric field, has two kinds of producers. An electric field can be caused by a positive or by a negative. A magnetic field can be caused by a north or by a south. So just like the electric field can be toward the producer or away from the producer, the magnetic field will also be either toward the producer or away from the producer, depending upon which pole you're looking at as the producer.